All right, hello everyone. Goal for this recording is to talk through the 4.1 to 4.4 quiz so that I don't have to do that in class. It allows you to kind of go at your own pace, stop me, slow me down, do what you need to do. So let's go ahead and get rolling. So let me get this out of the way here first. So first thing, absolute extrema. Absolute extrema are at the critical values and my endpoints. So I'm going to find critical values first. So my first step is to find the derivative. Sorry, that's enough. So derivative of this thing, power rule, 3 times 8 is 24. Decrease it by 1. 8 times 2 is 162. Decrease it by 1. And then the 42 is just 42. Okay, next thing. I want to solve this thing. So I want to set this thing equal to 0 and solve it. I'll go to my calculator. Because remember, this is calculator, okay? And I'm going to show you a little trick before I do that. I'm going to type in the function. So I had 24 x squared. And I would do this if I have more than one calculation that I need to do with the same equation. So 24x squared, actually, no, I'm not going to do that for this one. I'll do that for another one. Okay, so I want to find the derivative. No, sorry, I want to solve. So I'm going to go to menu. I'm going to go over here to algebra and then solve 24x squared plus 162 x minus 42 equals 0, comma, x. Now on the test, several people, like maybe 5 or 6, so more than just a couple, but several people found an x value that was outside the interval. So in order to kind of help me not fall into that mistake, I'm going to do this such that and limit my solving to -4 to 2, and that way I don't get an x value that is outside of my interval. So remember how I do that? I do the whole such that thing. So I do this second equal sign or control equals, and I click the such that, and then I do the -4 to 2, my interval. Hit enter. The only critical value is 1/4. Okay, so I'm going to go back. And when I solve that thing, so I solved 0 equals f prime of x, and I got x equals 1/4. So when you're doing these on a calculator, make sure you show your work, meaning make sure you show what you're typing into the calculator. So now I see, okay, this is what I solved, and this is what I got. Had this answer come out to be something weird, I would know that you knew what you were doing. You just made some mistake as you typed it into the calculator. Okay, so it's pretty important to show what you're trying to do. Okay, so now I'm going to do plug in 1/4. Whoops. I'm looking for absolute extrema. So my absolute extrema occur where I have the max value and the min value. So I want to plug in these endpoints and critical values into my original function. So I'm going to plug in -4, 1/4, and 2. Okay, so back to my calculator. And here's where I'm going to show you the shortcut. I think it's a shortcut. I don't know. I'm going to go 24. No, I'm not. Going back to f of x, I'm going to go 8x raised to the 3rd power, get out of the exponent, plus 81 x squared minus 42x minus 8. So there's my function. I'm going to store that. So I'm going to go control var, so the store is what I'm looking for, and I'm going to store that as f of x. I'm going to store it as a function. In pre-calc, we stored these sometimes as a variable, like an a or a b or something, but I'm going to store it as a function notation, and here's why. So now if I want to evaluate the function f at a bunch of different values, I can simply type them in. And I can do this very quickly without having to retype all the mess. It just evaluates all of these f values. Okay, so now I can go back to my deal and fill them in. So I have -4 was 944. 1/4 was a negative 13 point, where was it at? Negative 13.313. And 2 was 296. Okay, so clearly 944 is my max, and -13, etc. is my min. Whoops, sorry. Try that again. Okay, so there's my max and my min. All right. And just if I show all work that leads to my answer, this is enough work. My table shows that I calculated the function. Notation is important. I calculated the function at these different values. That's the biggest, that's the smallest. We're good. I don't need to show anymore. If you wanted to write -4, 944 is my max, that's probably more precise, I guess, or kind of summarizes it nicely. And remember, we're going to the nearest thousand, so 3 decimal places. Okay, so it'd be great if you did that, but the table is fine also. Okay, question 2. Relative min and max. So there's really no difference in my first step. I still have to find critical values. So before I start doing first derivative test, second derivative test, I'm going to find my derivative. So f prime is 3x squared minus 10x plus 7. I'm going to set that equal to 0, and you can go to the calculator and solve this, but we can also factor it. If you don't know how to factor well, I would spend some time factoring. So my first step is to get the 3x squared. My second step is to get the 7. My options are just 1 and 7. So the only things I can try are 1 and 7. And this product is added, since that's a positive, is added to this product. So 3, if I put a 7 here, 3 times 7 is 21. I already know it's too big, so that doesn't work. So I'm going to put the 7 here and the 1 here. 3 times 1 is 3. 7 times 1 is 7. And I get 3 plus 7, which is 10. So they both need to be negative because that's negative. They're both the same sign because that's positive. All those techniques or concepts from factoring. What makes this 0? A positive 7 divided by 3 and a positive 1 for that one. So there's my 2 critical values. Okay. In this case, I'm not going to make a table. I'm going to make a number line to help organize my data. That's the only purpose of the number line. It is not going to solve anything. It is just going to help me organize my information. Okay, so I'm going to plug in a value into my derivative that is less than 1, like 0. So plugging in 0, I go to factored form, it's easier. 0 times 3 is 0, minus 7 is a negative number. 0 minus 1 is a negative number. And a negative times a negative is a positive. Remember, I don't really care about the value, I just care about its sign. Something between 1 and 2.333, like 2. 2 times 3 is 6, minus 1 is still negative. 2 minus 1 is now positive. A negative times a positive is now a negative. Plug in something bigger than 2 and 1/3, like 3. 3 times 3 is 9, minus 7 is positive. 3 minus 1 is positive, and I get a positive. Okay, so this is f prime. Wouldn't it be nice if you could do what I'm about to do on a piece of paper? I need a little more room, so let's just slide that down. Okay, so I'm going to now just kind of do a little more organization. If my derivative is positive, that means my function is increasing. Now my function is decreasing. Now my function is increasing, so I can see maxes and mins very visually, in case I forgot. So I know that 1 is a max, so I need to know what is f of 1. So I plug 1 into here, and so on. So f of 1 is equal to 1 minus 5 plus 7 minus 5, which is what? Negative 2? Yeah. So f of 1 equals a negative 2. And I plug in 7/3. I'm going to cheat and use a calculator for that one because I can. Plugging in 7/3 gives me a negative 3.185. So I assume we can plug in 7/3 into our calculator. I did it earlier, and that's what I got. Okay, so we can start off by saying, let's do the max first. F of 1 equals negative 2 is a relative max because by, that's a keyword, linking what my statement is to how I know that statement. So it's a max because by first derivative, and a lot of you did a very nice job of writing this out, so I feel pretty confident on this one. Some of you just wrote by first derivative test. Now explain what that means. By first derivative test, since f prime switches from, there's an S on the end of that. Sorry, my writing's horrible. From positive to negative at x equals 1, it is a max. Okay, so by first derivative test, f of 7/3 equals negative 3.185 is a min, so I worded it a little differently, since f prime switches from negative to positive, we'll do it in words this time, negative to positive at x equals 7/3. Okay, so we have two statements. We have this one and we have this one. Worded a little different, but saying the exact same thing. You have to say what you know and how you know it. I know that this is a max by first derivative test because this f prime switches from a positive to a negative. Be careful. Don't say that f prime switches from increasing to decreasing. It does not. F switches from increasing to decreasing. F prime switches from positive to negative. And that's what my first derivative test talks about. It says since the f prime goes from positive to negative. Okay. Now, if you said since f switches from increasing to decreasing, you would probably be okay. I would give it to you, and I'm 99% sure that the AP folks, the readers, would give that to you also. But do what the first derivative test says. It says since the derivative is going from positive to negative at this value, it's a max. Okay. F increases, but and increases to decreases, f prime goes from positive to negative. Okay. There's one way. Okay, so I did it by the first derivative test for that problem. I'm going to erase all that work. So if you want to see it, you'll have to rewind. Okay, so this is all going away. So second derivative test. F double prime equals 6x minus 10. And so at 1, f, whoa, wrong notation. f double prime of 1 equals a negative 4, and f double prime of 7/3 equals, I'm going to cheat, positive 4. Okay, so now I can say by second derivative test, since, another connecting word, this is what I'm about to say, since f double prime of 1 is less than 0, f of 1 equals negative 2 is a relative max. By second derivative test, since f double prime of 7/3 is greater than 0, f of 7/3 equals negative 3.185 is a relative min. This means it's concave up, which makes that a min. This means it's concave down, which makes that a relative max. Two ways of doing it. Okay. I think that's okay. I was super impressed. A lot of you wrote that out very nicely. Okay, question 3. Find the value of C that satisfies the mean value theorem. Mean value theorem says if f of x is continuous on the closed interval, whoops, and differentiable on the open is defined on open. You could say f prime exists on the open, either one. Then there exists a C value where the average rate of change equals the instantaneous rate of change, somewhere in the interval. Okay, so I've already stated f of x is continuous on the closed, f prime of x is defined on the open. So I'm going to find f of 1, I'm going to find f of 4, and I'm going to find the average rate of change between those two values. So plug in 1. 1 squared minus 9 over 3 times 1 gives me, what, negative 8 over 3. Plug in 4, I get 16 minus 9 over 12, which gives me 7 over 12. So now y2 minus y1. Wow, what was that? y2 minus, a minus makes it plus y1 over x2 minus x1. Common denominator makes that a 12, makes that a 32, makes that a 39 over 12 divided by 3, which makes it, multiplying by the reciprocal, 39 over 12 times 1/3, which gives me 13 over 12. Okay, so I times this by 4 to get 12, so I had to times this by 4. That gives me 32 plus 7 is 39. Common denominator is 12. It comes across. Okay, so my average rate of change, now f prime, derivative of top, times the bottom, minus the top, parentheses, I got a lot of you, times the derivative of the bottom, all over the next thing, parentheses, the bottom squared. Combining some like terms, we'll go down here. I get 6x squared minus 3x squared plus 27 all over 9x squared. Combining more like terms, I get 3x squared plus 27 over 9x squared. Simplifying a little bit, dividing both by 3, I get x squared plus 9 all over 3x squared. So there's my derivative. So the average rate of change, 13 over 12, equals the instantaneous rate of change, x squared plus 9 over 3x squared, somewhere in the interval. Now let's find the x. Cross multiply. 13 times 3 is 39x squared. Cross multiply equals 12x squared plus 108. Subtract, I get 27x squared equals 108. Divide by 27, x squared equals 4. Take the square root, x equals plus or minus 2, but the one that's in the interval is x equals 2. Summarizing, state the fact that I can use mean value theorem. It is continuous on the closed. It is differentiable in the open. Now just work our way through. Find the two y values that go with those x values. Find the y2 minus y1 over x2 minus x1 stuff. Get my average rate of change. Find the derivative to find my instantaneous rate of change. Set them equal and solve. Okay, question 4. So this is a twice differentiable function. Okay, so this is my derivative of a function that's been taken the derivative of twice. Concave up, where is my second derivative positive? Concave down, where is it negative? Point of inflection, where is it equal to 0? So in both or all three cases, I need to know where it's equal to 0 and where it's increasing, decreasing, and so on. So I've already got it factored. That's super nice. So let's just put them on a number line so we can organize our data. So I get negative 2 makes this 0, positive 1 makes that 0, and a positive 3 makes that 0. Make sure they're in the right order from smallest to largest. Check values to the left of a negative 2, like negative 3. Again, I don't care about the value, I just care about its sign. So putting in a negative 2 makes that negative. No, sorry. Putting a negative 3 makes that negative. Negative 3 makes that negative. Something squared is always positive, so that'll never change. A negative times a negative is a positive times a positive is a positive. Put in something between a negative 2 and 1. Based upon what I learned last year in pre-calculus, it should switch signs, and this should be a negative. But let's just double check. Putting in 0. 0 minus 1 is negative. 0 plus 2 is positive. And a negative times a positive is negative. Plug in something between 1 and 3. I think this should be positive. So if I plug in something like 2, 2 minus 1 is positive, 2 plus 2 is positive, 2 minus 3 squared, that always is positive. Something bigger than 3, like 4, positive, positive, positive. Notice it does not change signs at 3. Why? Because this is always positive and it will not change signs at a squared factor. If my factor is raised to an even exponent, there will be no sign change from one side to the next. If it's raised to an odd exponent, there will be a sign change from one to the next. That's a pretty important concept from last year. Okay, concave up, meaning my second derivative is positive. Well, that'll happen from a negative infinity to a negative 2. Put that together with concave up. From 1 to 3, put that together with 3 to infinity. Now, just so you know, on AP Calc tests, they're not going to do that. They're going to go from negative infinity to a negative 2 and union that with 1 to infinity. They don't break at 3, okay? So they're going to go all the way, because that 3, is it still concave up? Well, that's just debatable. It's neither concave up nor concave down, but yeah, there's a big argument there. Same thing when we get to the whole, is it increasing or decreasing? But just so you're aware, if you're looking for a multiple choice, you're going to see this. If you did this on a free response question, you're not going to get it wrong, but you're going to see that on a multiple choice. Okay, concave down, -2 to 1. Negative second derivative, -2 to 1. Okay, points of inflection. Points of inflection are where my second derivative is 0 or undefined. And remember on the board yesterday, well, last time we were here, well, the day before the test, I had this in big, bold, capital letters. It's where my second derivative is 0, undefined, or and, switches signs. So it's 0 at -2, at 1, and at 3. At -2, it switches signs. At 1, it switches signs. At 3, it does not switch signs. It stays concave up on both sides. 3 is not a point of inflection. It is a critical value. It is where my second derivative is equal to 0. It is not a point of inflection. It does not switch concavity. Okay. Question 5. There's a lot going on in question 5. Being able to read a graph is super critical. So we're going to talk through this one pretty thoroughly. So f is some function that's differentiable and is increasing for all real numbers. And the graph has exactly one point of inflection. So let's work our way through those 3 statements. So make sure we are knowing what we're looking at. The function f is differentiable. And this is my derivative graph. So f is differentiable. What does that mean in the derivative graph? If f is differentiable, there will be no holes and there will be no asymptotes. There'll be no break in the graph. It'll be continuous. These are all continuous graphs. This does not eliminate any of these graphs. Now, some of you might be saying, well, wait a minute, that is a cusp, so it's not going to have a derivative. Correct. This is the graph of my derivative, so this second derivative won't exist, but that's not what it says. It says f is differentiable. Yep, it is differentiable. I got a value for every single x-coordinate in the derivative. The second derivative, there's going to be something going on here where there's a break in the graph. Okay, increasing. If f is increasing, what does that tell me about f prime? If f is increasing, f prime is greater than 0 for all real numbers. So no matter where I'm at, f prime will be above the x-axis. It'll be greater than 0. The actual values of my derivative will be greater than 0 because my function is increasing everywhere. This is all above the x-axis, so this one's good. This one dips below the x-axis. This one's gone. This one dips below the x-axis. This one's gone. This is always above. This one's still okay. So these two are still options. Now, most of you picked B as your correct answer. Do you see why now that this fact makes B impossible? F is strictly increasing. F prime being below the x-axis says the F prime values are negative, and if the F prime is negative, my original function is decreasing. Okay, so let's go to the next part. The graph has exactly one point of inflection, meaning my second derivative is equal to 0 and it switches signs. Okay, so this is the graph of the first derivative. I'm looking at these two only. This is the graph of the first derivative. So my second derivative, sine, will tell me whether the function's increasing or decreasing, or vice versa. If my derivative is decreasing, my second derivative will be negative. So this has a negative second derivative from here to here. F prime is increasing from here on. So then the second derivative will be positive. Negative second derivative, positive second derivative, undefined second derivative, whatever this point is right here, is a point of inflection. It switches from concave down to concave up, from decreasing first derivative or negative second derivative to an increasing first derivative, which means a positive second derivative. Okay. We could talk about this one just for the fun of it. This has a negative second derivative to here and a positive second derivative to here. So this does satisfy having exactly one point of inflection. But it doesn't satisfy this increasing for every value of x. Okay, let's go to here. So far, A looks like the choice. Okay, so I know that's meeting all the criteria so far. So my guess is this is going to fail. So I go from increasing to decreasing, and this has a horizontal tangent. So f prime is positive here, it is 0 here, it is negative here. It is 0, another horizontal tangent, here, it is positive here. These two are 0 second derivatives, and they both switch signs, so there are 2 points of inflection. Points of inflection occur where your first derivative has a max, relative, max, or min. Yes, this is not defined, but it is still a relative min. This point is the lowest y value of any in the area. This is a relative min, point of inflection. This is a relative max, it's a point of inflection. Relative min, it's a point of inflection. Okay, but I only wanted one, so question or answer A, option A, is my answer. This one has no points of inflection, in case you're wondering. All right. Question 6, probably the one that we didn't like the most, or that we liked the least. So you've read it, so I don't need to read the whole entire thing. I'm going to define number of people, n of t, to be f of t minus g of t. So the number of people in the museum is equal to the number of people who have left minus the number of people who have, arrived minus the number of people who have left. Okay? So this is the number of people. So n prime of t is going to be f prime of t minus g prime of t. So the rate at which they leave, the rate at which they are in the museum, or the rate at which the number of people is changing, is equal to the rate at which they arrive minus the rate at which they leave. The rate at which the number of people is changing is equal to the rate at which they're arriving minus the rate at which they are leaving. That's how the number of people is changing. Okay, so when will there be a maximum number of people? So when is this a maximum? When my derivative is equal to 0 and where it goes from positive to negative, doing the first derivative test. Okay, so let's go back to our equation, our calculator, and let's solve that equation. Oh, sorry. Let's solve, I need to show what I'm doing. Let's solve that equation. Okay, so and I want to write that so that my readers, whether it's me or an AP reader, can see exactly my thought process. I'm going to set the derivative equal to 0 to find max and mins, critical values. All right, so I'm going to go to solve, menu, algebra, solve, and I'm going to type that big, huge mess into my calculator. Sorry, I got to switch pages so I can read it off my quiz. F of x was 380 times 1.02 raised to the x power, get out of the exponent, minus 240, be careful, I'm distributing the negative sign, minus 240 sine. I like this fraction button better, so go control, and then this guy, no, sorry, don't go control. Go this guy right here. Nope, didn't mean to do control. I'm going to do this right here. Why is it doing that to me? I don't want that there. For some reason, my calculator has got a mind of its own right now. I'm going to hit pause and retype all that mess in. All right. Sometime, for some reason, when I click on that, sometimes it locks and it just starts deleting the whole entire thing. All right, so I'm going to go, again, push this button right here, and over here gives me the horizontal line for a fraction instead of the diagonal. So I'm going to use this one just because I can see it better. So I'm going to go pi. Yeah, once again, it just is getting a mind of its own. All right. Parentheses x minus 4. Go down to the bottom, type in 12. Now, since this is a trig function, I definitely want to do the such that, oh yeah, sorry, equals 0, comma x. Now get out and do such that. So control and go back to, no, I want to go from 1 I want to go from 1 to 11. So I have my equation typed in, minus 240 sine, just double checking I have everything before I hit equals 0, comma x, go from 1 to 11, hit enter, and I get two values. Okay, 7.888 and 10.974. I'll go back to my deal. So my two options are t equals 7.888 and t equals a negative 10.974. All right, so here was some of the frustration from a couple people. There is no function for f of t and g of t, so I can't use the extreme value theorem saying that if I plug these, I can use the theorem saying there is going to be one, but the whole check endpoints and critical values, I can't do that because I have nothing to plug it into. So I'm going to have to do a little interpolation, because I'm inside the interval. I have to do a little interpolation or a little interpreting my data. Okay, and I'll show you what I mean by here in a second. So we have a 1, we have cruising way over here, we have 7.88, cruising a little bit further over, we have a negative 10.974, and then right next to it, we have 11. If we're going to kind of try to make this number line to scale, it's not perfectly to scale, but you get the idea. There's a big gap between 1 and 7.88, not quite as big a gap here, and then a microscopic gap, like 0.03 gap between this point and this point. Oh, wait a minute. Why do I have a negative? I don't mean a negative. Okay. And I don't mean a negative there either. Glad I caught that. Okay, so next thing. Let's plug in values in these intervals to see where it's increasing, decreasing, and let's at least find relative mins and maxes. Okay, we can at least do that, and we can talk about how to find out if they're absolute or not. So plug in something between 1 and 7.88, like 2. And I'm going to plug it into my derivative graph because I want to know where my derivative is positive and negative to show whether the original function is increasing or decreasing. Are more people leaving or more people entering at that point in time? Okay, is the number of people increasing or is the number of people decreasing at that time? Okay, so plug in 2. And I'm just going to tell you when I plug in 2 into that function, it comes out to be a positive number. And I assume you can plug in 2 and work it out. I'm going to plug in 8, something between here and here. And when I do that, it becomes a negative number. And when I plug in something between these two, it comes out to be a positive again. Okay, so it looks like I have a relative max here, and I have a relative max possibly at 11, but I don't really know at the 11. But I have a min at 10.974. Okay, so at time equal 1 to time equals 7.88, my graph is increasing for that entire time, meaning the number of people is increasing from 1 to 7.88. So for 6.88 seconds, no, hours, for 6.88 hours, my number of people in the museum is increasing. At time equals 7.88, now the number of people in the museum starts to decrease for about 3 seconds. Then at 10.974, it stops and goes up for just a fraction of a second. So the question is, which is bigger, this number or this number? Well, this only increased for a tiny little bit. This increased for all that time. So this is going to be a larger value than this. 7.88 is a max. Can I say that with certainty? Yeah. And here when we get to integration in a couple months, not even that, about a month and a half, we'll be able to do something called integrating to find out the total amount of people that have increased and the total amount of people that have decreased and so on. For right now, we just have to use a little interpretation. All right, I hope that helped. I shouldn't have put that on here. It should have been more of one like question 1, where there is a function and you can plug it in, you can actually find the number of people. So I apologize for that one. All right, it was a good talking point though. Questions 7 through 10. Super important graph. And unfortunately, this is where a lot of us struggled. So we definitely need to talk through this one. First thing, what is this a graph of? Graph of f prime. Okay, super important to know, what am I looking at? Okay, so the graph above shows f prime. It is twice differentiable, simply meaning I can take the derivative of every point on this graph. Next thing, it is going to end at -3 and at 4. There's nothing to the right and there's nothing to the left, or at least I don't know what's to the left and to the right. Okay, we have horizontal tangents. They're just telling us we have horizontal tangents at these different points. Sorry, I've been talking for a long time. Question 7. On what intervals is the graph both concave down and decreasing? So let's do one at a time. Concave down. This is my first derivative graph. We've already talked about this back in question 5. My derivative of the derivative tells me my second derivative. So where my f prime is decreasing, f double prime is negative. So f double prime is negative from a -3 all the way to a -1. And my original function is concave down over this entire region. So this is f double prime. F double prime is negative, implying that f is concave down from a -3 to a -1. Why? Because f prime is decreasing, the value of its derivative will be negative. Same logic. From a -1 to a +1, my f prime is increasing, so f double prime is positive, making f concave up. from 1 to 3, f prime is decreasing, making f double prime negative, making f concave down. Notice how it's super important that you can convert and interchange, or not interchange, you can convert between and you can make statements about f, f prime, f double prime, depending upon a given graph. Okay, lastly, from 3 to 4, f prime is increasing, so f double prime is positive, which makes f concave up. So we've taken care of concavity. Decreasing. Where f is decreasing is where f prime is negative. Where f is decreasing, f prime is negative. This is f prime. F prime is below the x-axis, or negative, from -2 to 4, except at 1 where it's 0. So where is it both concave down and decreasing? Everywhere that it's concave down below the x-axis. So from a -2 to a -1. So from a -2 to a -1, unioned with from 1 to 3. It is both decreasing and concave down. Okay? You could say, give a reason, because f double prime is negative and f prime is negative at those places. In words, f double prime and f prime are both negative. Okay, number 8. Points of inflection. Well, we kind of already talked about it. Here's where my graph is switching, so it goes from negative, my graph, meaning, sorry, I gotta be more specific. Points of inflection, where my second derivative is 0 and where it switches signs. So we already did this. Second derivative is 0 right here, right? Because it has horizontal tangents. F prime has a horizontal tangent, meaning f double prime is 0. Here, here, and here. So at x equals, these are my options, at x equals -1, +1, and 3. Does f double prime switch signs at those places? Yeah, because it goes from negative to positive to negative to positive. It goes from negative to positive to negative to positive. They switch signs at those places. Remember back in question 5, we said points of inflection occur at max and mins of my first derivative. Points of inflection occur at mins and maxes of my first derivative, because my slope of that line goes from negative to positive. So my second derivative goes from negative to positive, to negative to positive. It switches signs. Those are points of inflection. Number 9. We already talked about this one. Where is f increasing? Where f is decreasing is where it's negative, so where f is increasing is where it's positive. Where is f positive? From a -3 to a -2. Sorry. Where is f prime positive? From a -3 to a -2. F prime is above the x-axis from a -3 to a -2. That's it. So where is it increasing? From a -3 to a -2. That is the only place it is increasing. Where is it decreasing? Everywhere else. From a -2 to to +4. Now if you split it up and you went -2, was it a 1? If you went from a -2 to 1 and union that with 1 to 4, that's fine. but again, the AP folks on a multiple choice are going to go -2 to 4. More than just the AP folks. I got to can't keep blaming them. There's a chunk of the math community that goes here, and there's a chunk, I'm kind of in this camp, that goes here. That's a whole other debate. I'm not going to spend time in this one talking about all that. But it's a good debate, but I'm not going to spend time talking about that right now. Okay, question 10. Relative extrema. First derivative test, where f prime goes from positive to negative is where I have a max, and where f prime goes from negative to positive, I have a min. So, where my f prime crosses the x-axis is where it's 0. So it crosses here and kind of crosses, it touches here. So my possible extrema are at -2 and 1. My critical values are definitely at -2 and 1. So my options are x equals -2, so my options are x equals -2 and x equals 1, because that is where my first derivative is 0. And relative extrema occur where my first derivative is 0 or undefined. Okay, does it switch signs? My first derivative goes from positive, it's above the x-axis, to negative, it's below the x-axis. It goes from increasing, it meaning the first, or the original function, goes from increasing to decreasing. This is a relative max. My first derivative stays negative. It goes from negative to negative. My original function is decreasing, and it is still decreasing. This is a plateau point. So if I'm graphing it, it's going to go up until it gets to -1. Then it's going to go down, not quite that steep. Then it's going to go down until I get to 1. It's going to flatten out for a second, then keep on going down. Decreasing, flatten, decreasing. Flatten meaning it goes to 0 for just a second. So this is not a relative extrema. This is called a plateau. I don't think I'd even say it, because now they might think, oh, he thinks or she thinks that this is a relative extrema. Nope, that is my only one. This is a plateau point, does not need to be listed. Should not be listed. Okay, there is the quiz. Hopefully that recording helps. All right, almost an hour. Sorry, I got long-winded.